You know, there is a question so strange that most physicists do not dare ask it aloud. And the question is this: what if there is only one electron in the entire universe, and it is simply very, very busy? My name is Albert Einstein, and I have spent a great many years contemplating the architecture of reality. And I can tell you, this idea has haunted me since the moment I first heard it from a colleague at Princeton. But before I take you deeper into this strange possibility, I want to tell you about something I have put together for minds that refuse to settle for the simplified version. If you have ever watched a physics documentary and felt that something was missing, that the real depth was being hidden behind a curtain of easy metaphors, then you understand exactly why I created the Reality Decoder Bundle. It is a collection that walks you through the truth about gravity, which is not a force at all, the hidden architecture of light, why time does not flow the way you feel it, the quantum reality happening inside your own cells, why your brain lies to you about reality, the science behind practices like humming and grounding, the brutal physics of deep space travel, the silence of the universe, and finally how consciousness emerges from all of it. All in plain language with no equations. The link is in the pinned comment right below. Now let me tell you about the electron. The idea came from John Wheeler. Wheeler was not a man you dismiss lightly. He was the physicist who gave us the term black hole, who sat across from me at Princeton and argued with me face to face about whether quantum mechanics was complete, and who trained Richard Feynman. Training Richard Feynman is no small thing. So when Wheeler said something that sounded like poetry dressed up as physics, you did not laugh. You went home. You thought about it for decades, and eventually you either decided he was wrong, or you decided the universe was stranger than you were prepared for. I have not yet decided. That is why I am standing here. Let me back up, because before I can tell you what Wheeler was reaching for, I must tell you something about electrons that most people walk past without stopping. Every electron in the observable universe, all 10 to the 80th of them, give or take, is absolutely, perfectly, completely identical, not similar, not nearly the same, not the same with an experimental error, identical. Same mass, same charge, same magnetic moment, same spin. You take an electron from a hydrogen atom sitting in a laboratory in California, and you compare it to an electron from a hydrogen atom sitting in a galaxy 12 billion light years away, and you will not find a single difference. Not one. The electron does not have a serial number, it does not carry a history, it does not age, it does not wear out. Every electron is every other electron, and has been since the beginning of time. Now I want you to stop and ask yourself why. Why should that be true? Because it is not obvious. There is no law written on the wall of the universe that says all fundamental particles of a given type must be perfectly identical. You can imagine a universe, mathematically coherent, where electrons come in slightly different flavors, where the electron that spent the last billion years inside a red dwarf star is a little different from the one drifting through intergalactic space since the Big Bang. You could imagine that. But that is not the universe we live in. In our universe, they are all the same. And that sameness is so precise, so absolute, so unbroken across the entire history of the cosmos, that it demands an explanation. Or at the very least, it demands that you feel the weight of needing one. Most physicists, when pressed on this, will tell you that the identical nature of electrons follows from quantum field theory. And they are right. In quantum field theory, you do not think of electrons as individual particles bouncing around. You think of them as excitations of a single underlying field, the electron field, that permeates all of space and time. An electron is not a thing that exists and moves. An electron is a ripple in a field, and every ripple in a given field has the same properties because it is the same field. That is why they are all identical. The field is the thing. The particles are just what the field is doing in a particular place at a particular time. That is a satisfying answer. It has mathematical precision behind it. It works. And yet, and I say this as someone who has worked inside quantum field theory, it leaves something unsaid. It tells you the mechanism. It does not tell you why the mechanism works the way it does. It does not tell you why the field has the properties it has and not some other properties. Quantum field theory describes the universe. It does not explain it. That distinction matters, and the day you stop caring about that distinction is the day you stop doing fundamental physics and start doing engineering. So we have this fact, perfect identity, and we have a description of the fact. And somewhere between those two things, Wheeler had an idea. Here's where it becomes strange. Wheeler's idea was this: The reason all electrons are identical is that they are, in literal fact, the same electron. One singular electron, moving through space and time in such a way that it appears, from our vantage point, to be everywhere at once. And the reason it appears everywhere at once is that everywhere at once is exactly what a single particle looks like when it is weaving back and forth through time. Forward into the future, backward into the past, crisscrossing itself again and again, until what you are looking at is not a single trajectory, but a kind of cosmic tangle that from any given moment in time looks like a nearly infinite number of particles sitting side by side. Wheeler did not keep this idea to himself, he told Feynman. And Feynman, who was Wheeler's graduate student at the time, and who was even then already one of the sharpest minds in the room, took the idea and did what Feynman always did. He checked it. He turned it over. He looked at it from every angle. He found what was beautiful about it, and he found what was wrong with it. And then he told Wheeler what was wrong with it. And Wheeler, who was a great enough physicist to take that kind of correction from a graduate student, listened. What Feynman pointed out was this. If a single electron is weaving back and forth through time, then every time the electron moves backward in time, it behaves like an anti-electron, what we call a positron. The positron is the antimatter counterpart of the electron. Same mass, opposite charge. They annihilate each other when they meet. Now a single electron weaving through time would produce, at any given moment, roughly equal numbers of forward-moving segments, electrons, and backward-moving segments, positrons. Which means if Wheeler's picture is right, there should be approximately as many positrons in the universe as there are electrons. And there are not. There are, as far as anyone has been able to measure, vastly more electrons than positrons. The universe is almost entirely made of matter, not antimatter. That asymmetry is one of the deep unsolved problems in cosmology, and it sits directly in the path of Wheeler's one-electron universe. Feynman told Wheeler this. Wheeler, to his credit, said something like, "Perhaps the extra positrons are hidden inside protons." This was not a satisfying answer. It was a holding maneuver, a placeholder. The kind of thing you say when you are not ready to abandon a beautiful idea, but you cannot yet answer the hard question. I have done it myself more times than I would like to admit. You hold on to the beautiful thing, and you keep working, hoping the hard question will eventually yield. Sometimes it does. Sometimes the beautiful idea turns out to be right in ways you did not initially understand. Sometimes it turns out to be wrong in exactly the ways that were pointed out to you 30 years earlier. Physics is not a linear process. It is a messy, recursive, humbling process. So where does that leave us? We have a beautiful idea, one electron, threading through time. That has a serious empirical problem. That problem is real. I am not going to wave it away. But I want to argue that the idea, even if it is not literally true in the way Wheeler imagined it, is pointing at something that is true. The intuition behind it is sound, even if the specific implementation is flawed. And to make that argument, I need to tell you about the mathematics that Wheeler was, whether he knew it or not, reaching toward. In 1928, Paul Dirac wrote down what is probably the most beautiful equation in the history of physics. I say that knowing there are people who will argue for Maxwell's equations or for my own field equations, and those are extraordinary. But the Dirac equation is something else. It is the equation that describes how an electron moves relativistically, meaning it respects the rules of special relativity. And what Dirac found when he solved it was that it did not just describe electrons, it described something else. It predicted the existence of something with the same mass as an electron, but with opposite charge. It predicted the positron before anyone had ever seen one. Carl Anderson found the positron in cosmic ray experiments in 1932, 4 years after Dirac wrote down the equation. That is what a good physical theory looks like. It does not just describe what you already know, it tells you what is there before you have looked. Now here is what the Dirac equation is actually doing that matters for us. When Dirac wrote down his equation, he was trying to reconcile quantum mechanics with special relativity. And to do that, to write a wave equation for an electron that satisfied Lorentz invariance, he found that the equation naturally mixed together what we would call particle states and antiparticle states. They were not separate things in the mathematics. They were two sides of the same solution. The electron and the positron were not two different objects that happened to have related properties. They were two aspects of a single mathematical object, a spinor, which is a mathematical structure that transforms in a particular way under rotations and Lorentz boosts. The electron and the positron are in a deep mathematical sense, the same thing, just with different orientations, in an abstract space we call spinor space. This is not metaphor. This is not poetry. This is mathematics. And now I want to connect this to Feynman, because Feynman took Dirac's mathematics and did something extraordinary with it. What Feynman realized, and this is the insight that eventually became the foundation of quantum electrodynamics, which is the most precisely tested theory in the history of science, is that you can describe an electron moving forward in time and a positron moving forward in time as two different interpretations of the same underlying mathematical path. A positron moving forward in time is mathematically identical to an electron moving backward in time. Not physically identical, I want to be careful here, but computationally, mathematically, for the purpose of calculating what happens in a given interaction, you can treat them as the same thing with a different time direction. Feynman used this to simplify his famous diagrams. That is why in a Feynman diagram, you draw an electron line with an arrow on it, and when that arrow points backward in time, it represents a positron. Same line, same particle, different direction. This is Wheeler's one-electron idea dressed up in mathematical clothing that actually works. If this is hitting home, and you feel the weight of what we are uncovering here, the full reality decoder bundle is in the pinned comment. It goes deeper into these questions, into the nature of time, into why your brain constructs the reality you experience, and into the hidden architecture of the universe that most explanations skip over. The link is waiting for you. Now, here is where it becomes strange again, and I mean this in a deeper way than the first time I said it. If Feynman's formalism is telling us something real, and I believe it is, because the predictions it produces are accurate to 10 significant figures, which is better accuracy than measuring the width of North America to the width of a human hair, then what it is telling us is that the distinction between particle and antiparticle, between matter and antimatter, is not a fundamental distinction. It is a perspective, it is a choice of how you orient yourself relative to the direction of time. The electron is not a fundamentally different thing from the positron. It is the same thing seen from a different temporal angle. And if that is true, if the particle-antiparticle distinction is really just a question of which way time is pointing, then we are looking at something deep about the structure of time itself. Because here is what that implies. It implies that time as a direction, as a thing that points from past to future and not the other way around, is not built into the fundamental laws. The fundamental laws of quantum electrodynamics are, to an extremely good approximation, time symmetric. Run the equations forward, run them backward, they give you the same physics. The arrow of time, the fact that eggs break but do not spontaneously reassemble, that you remember the past but not the future, that entropy increases, that arrow is not in the microscopic laws. It emerges. It is a statistical thermodynamic feature of how large collections of particles behave, not a fundamental feature of what particles are. And if time does not have a built-in direction at the level of individual particles, then forward and backward are not absolute. They are, in some sense, chosen. And if they are chosen, then the distinction between an electron moving forward and a positron moving backward collapses into a single trajectory, with a single identity seen from two different vantage points in time. I want to be honest with you about how far this argument goes and where it starts to become speculation rather than physics. What I have just described, the time symmetry of the fundamental laws, the mathematical equivalence of electrons and positrons in Feynman's formalism, that is established physics. That is not controversial. What is more speculative is the jump from that established physics to the claim that there is, in some operationally meaningful sense, only one electron. That jump requires you to accept that the mathematical equivalence is more than a calculational convenience. It requires you to believe that when we say the same particle, different time direction, we are describing the actual metaphysical situation, not just a useful fiction. I have colleagues who would tell you that question is not a scientific question, that it is a philosophical question, a question about interpretation, not about predictions. And they are not entirely wrong, but I think they are being too quick to close the door. Because there are physical questions that only come into focus if you take the underlying structure seriously. Questions about the nature of identity in quantum mechanics. Questions about what information means in a universe where particle and antiparticle are related by time reversal. Questions about whether the initial conditions of the universe, including the matter-antimatter asymmetry that bothered Feynman, have an explanation that lives at this level of structure rather than being imposed from outside. Let me tell you about a conversation that changed the way I thought about this. It was with Gerard T. Hooft, the Dutch physicist who shared the Nobel Prize for his work on the renormalizability of gauge theories. 't Hooft is one of the few people who has thought as deeply about the foundations of quantum mechanics as anyone alive. We were discussing the Wheeler idea, and he said something I have not been able to forget. He said that the one-electron universe fails observationally, but it succeeds conceptually. It succeeds because it forces you to confront the fact that the identity of a particle is not a given. It is not a primitive. It is something that has to be explained. And the explanation, whatever it turns out to be, will likely involve time in a way we do not yet fully understand. So where does this leave us? The universe has only one electron. That is the claim. The physics proves that it is mathematically coherent. The physics proves that it is consistent with the equations we use every day to describe reality. The physics proves that the distinction between an electron and a positron is a distinction of temporal orientation, not of substance. But the physics also proves that the universe we live in does not look like a single electron threading through time. It looks like 10 to the 80th electrons and far fewer positrons. And that mismatch is not a small detail. It is a clue. The Wheeler idea is not the answer, but it is a mirror. It reflects back to us the strangeness of the identity of particles, the strangeness of time, the strangeness of the fact that we live in a universe where matter dominates antimatter. And maybe, just maybe, the reason the idea refuses to die, the reason it keeps resurfacing in conversations between physicists, is that it is pointing toward a deeper structure that we have not yet fully articulated. A structure in which time is not a line but a weave. A structure in which identity is not a property of particles but a property of the entire history of the cosmos. A structure in which the electron you see in your laboratory and the electron that was born in the first moments of the universe are, in the only sense that ultimately matters, the same. Before I leave you, I want to invite you to the pinned comment one last time. The Reality Decoder bundle is there. It takes you deeper into every idea we have touched on today, from the nature of time to the silence of the universe, from the quantum reality inside your own cells to the brutal physics of deep space travel. It is for people who want the actual depth, not the simplified version. The link is in the pinned comment. And now, I leave you with this thought. The universe may not have only one electron, but the fact that we can even ask the question, the fact that the mathematics allows it, the fact that the idea refuses to be dismissed, tells us something about the universe that we are only beginning to understand. And that is worth thinking about for another 20 years.